All right, good afternoon, everybody. Happy Tuesday. How's life? It's okay. It's interesting. Are those related in any way?
It's busy.
It's busy. Yeah, sorry. So let's see. Tomorrow's Halloween. Is that good? Does anybody care? Yes, some people care. Okay. Why do you care so much? Why is it like, yay? Are you all going to be dressed up? And I'm not going to be here to see what kind of ridiculousness goes on. No. Candy? Candy happens all day tomorrow. You know you're old enough you can buy your own candy now. You can have as much candy as you want all the time.
But the
That's
best
fine.
day is the day after Halloween.
Oh. Yeah, that's kind of good for all major holidays. Like Easter, then you go to like CVS the next day. Yeah. Yeah. That's a good point. Christmas. Do you get turkeys on sale after Thanksgiving? So good. All right, so first of all, we've got today, then Thursday, and then Tuesday, Thursday, and then Tuesday exam on Thursday. Okay, so we've got 4 total lectures, including today, with new stuff, and then we'll have 1 day for review, and then we'll have an exam right before we get our week off. So we're very quickly kind of coming down the home stretch here. So we've got these 3, and I think there's 3 full weeks after the fall break. Does that sound right? Ish.
Well, yeah, if you count on it,
I don't know. Something kind of like that. I thought it was 3 full class weeks, but I could be wrong.
Yeah, technically, no, yeah.
Yeah. So we've got essentially 10-ish lectures left. Maybe even 9 with just new material. 9, 2 review days, and an exam, if that sounds about right. That's just nothing, right?
Yeah.
We should just quit now. There's no way we can learn it all.
I know, yeah.
Just stop. Okay, we're out of here. That's it. Goodbye. No. Let's see. So I don't know how far we're going to make it before this exam. I need 4 lecture days. We're finishing up most of chapter 28 today. We're not going to have time to get through all of it, so we'll finish 28 for sure on Thursday. I've already created the homework assignment for that chapter, and it's due a week from Thursday. Okay, so that's already kind of sitting and floating out there. Ideally, we are going to do at least 2 of the problems in class today and Thursday out of the 10 problems that are there. So, yay, 20% of your homework will be completed. The thing is, I'm still going to make you do it. You're just going to do it in class. So, prepare yourself. In like 20 or 25 minutes, we're going to stop and you all are going to work a problem. And then I'm going to talk some more, and then you're going to work another problem, assuming we don't run out of time before all that happens. That's kind of my goal, though, but we'll see how that goes. So let's go back in time a little bit. We were rushing through this section just a little bit, starting to talk about resistors in circuits. So I want to review how they behave in series, as well as add just a little bit of what might be helpful information. Then we'll talk about putting them in parallel, and we're going to do an example circuit, and then that's what you people are going to do, is work another circuit yourself, okay? So resistors in series, keep in mind, if they are in series, that means that one comes right after the other, as you see on the top right, which leads to this idea that they all have to have the same current passing through them. The current has nowhere else to go. It goes through the first resistor, and then the second one, and the third one, and the fifth one, and the 10th one, however many you may happen to have in series, okay? They all have to have the same current passing through them. However, they may have a different potential difference or voltage across each of them. So between this point just before resistor 1 and this point just after resistor 1, that's going to have a different potential difference than from before resistor 2 to after resistor 2, and so forth, okay? We call each of those potential differences or voltages just with a subscript that denotes which resistor we're talking about. So we have V1, V2, and V3, okay? We worked through this whole little sequence here that led us to the idea that when I combine resistors in series, you just add them up, okay? More resistors in series gives me more overall resistance, okay? Now, here's what I wanted to add. I inserted a slide here, and I'm going to redraw the circuit to kind of give you maybe a better feel for what's happening, okay? So I'm going to draw it vertically. So let's start with something that looks like this. And we're going to make it look a little bit more like the person with the bucket of water, you know, that type of circuit. We're going to kind of draw it in that configuration if it helps. And we're going to say that essentially the battery brings the potential up. It's doing work to get things to a higher potential, to bring those charges to a higher potential energy so they're ready to, say, fall down to a lower potential energy once again. So if you were to think of that as water, think of the battery as sort of a water pump, something that pumps it up to a higher height, okay? And then we're going to say that the first resistor results in the potential dropping, okay? By the time I've gone past the first resistor, it's the equivalent of, say, some of the water being at this height going down a little waterfall, if you want to think of it like that. And now it's at a new level, okay? So this maybe is resistor 1, and we're going to say from here down to there is V1. It's how much the potential drops as the current passes through that resistor. So literally, we often use the term voltage drop and use this analogy sort of just in the lingo talking about these sort of things, okay? So how much does the potential or the voltage drop as you go from one side of the resistor to the other, okay? Now we get to the next resistor, and we're going to keep things in series, meaning like it can't go anywhere else. It's still along the same path, but I'm just going to sort of step it over to the side a little bit so we can see it easier. And here maybe we have resistor 2, and maybe it has less resistance. So you'll notice I drew a drop that wasn't quite as far, okay? If the same current is passing through both of these and this has less resistance, Ohm's law, V equals IR, tells me that there will be less V that gets used because of that current and that resistance, okay? The thing is, by the time I get all the way back to where I'm ready to be pumped back to the top again, all of that voltage has to be consumed. So here is resistor 3, and from top to bottom of it is voltage drop V3. And you'll notice now I'm all the way back down at ground level, which we might call the location where V is equal to 0. Let's get rid of some of these lines. Maybe put a dotted line here like that, okay? So think of it as a loop where the voltage goes up to a higher level, the battery does that, and then as resistors are in play, each one of them sort of uses up is a bad terminology, but say from one side to the other, the level of the voltage or the level of the height is dropping to new levels. By the time I get connected back to this lower side of the battery, well, I should be all the way back to 0 for it to go around another loop, okay? Does that help clarify kind of a little bit about what's happening with the voltage as you go around a circuit? And just looking at this, think about the current. Again, it has nowhere else to go besides just like flow right through all of these and work its way back around. That's the only option the current has. That's the only path it can go through, okay? Now go back and think about that in light of our circuit that looks just like this. You can almost view it sort of three-dimensionally if you're careful, right? Think about that waterfall and just imagine that all of these spaces here are all the way at the top, the highest potential, and then this goes down to a little bit lower potential, and then this goes down to a little bit lower, and then this goes all the way to the bottom and waits to be pumped up to the top again, okay? Got it? Got questions? I can't promise I have answers. Yes, in the back.
So I guess if all three of the resistors are the same, it would just essentially be the same thing as doing 3 times R.
Yes.
Okay.
Yeah. Typically they won't be.
Yeah.
And each one just proportionally uses up its share of the voltage. Okay? There was a question here. Yeah.
Does the same thing happen, or does something similar
Without resistors, it's a little bit difficult. Without resistors, yes, it has to. But if we assume that there's no resistors, we often assume that the wire has zero resistance. You start to get a situation where we're saying that zero resistance is there, which means the current is infinite, which isn't really true. So even if there's just wire, technically there's some resistance there. It just may be a very small resistance. And then you end up with a circuit that's, it's the same thing. It's just that it's the resistance of the wire that we draw in instead of like a separate resistor. Okay? So there's always going to be some resistance there. I saw another hand, I think. No? Okay, let's talk about parallel resistors. Let's go over to here and how they behave, and then we'll be ready to actually try one of these problems. Okay, so let me start by, let's look at this circuit up on the top right. And let's think about what the current does. It starts here on the positive side of the battery. You can see they already drew the current in for you. It gets to this particular point at which it has some options. It can go down the top branch or the middle branch or the bottom branch. And you can see they've labeled those current 1, current 2, and current 3 because there are resistors 1, 2, and 3 in the 3 branches, okay? So some of the current goes this way, and some of it goes this way, and some of it goes that way. And it's literally being split. It's like you started with a total amount, and whatever is in those 3 branches all has to add up to give what was going into that split location. Not really unlike a stream of water, right? If there's a big wide river, and all of a sudden there's 3 different ways for the river to go, some of the river goes down each branch, but if you add them all back together, you get the original river again. Question?
So we're splitting these, for example, these 3 currents, would they be split equally in 3?
Only if the resistors are equal. Okay? So typically they're going to be different. Now, notice what happens at point B. They all come right back together. Okay? They get reassembled so that when I get over to this other side, we're back to just the total current I once again. Okay? So when I have resistors in parallel, we can say that they may have different amounts of current, so different I, and it will be different as long as the resistors are different. It's only the same if the resistors are the same. But the thing they have in common is the voltage. So we'll say that they do have the same V. And I'm going to explain that in a couple of different ways, all right? So they do have the same potential difference. If I go back over to this diagram, once again, just take a look at all of this wire that's sort of like in this whole region here, from the positive side of the battery all the way to the left side of all of those resistors. That is all one conductor. It's all the exact same conductor. You could say that it is an equipotential surface, and all points on it have the same potential, okay? Every single point on every part of that wire on the left-hand side has the exact same value for the potential, okay? Over here on the other side, like everything that's inside that region is all the same conductor. It's all just wire connected to wire, just sort of going out different directions, okay? So here, all points have the same potential. And they're not going to be the same. We're going to have a different, higher potential over here where it's connected to the positive side of the battery, and a different, lower potential where it's connected to the negative side, okay? But the thing is, whatever the difference is between all of these points of wire over here and all these points of wire over here, it's going to be the same. all of it is the same potential difference, okay? So when I go and look at this circuit and think about between right here and right here, what I might call V1, which you can't quite see for whatever reason. So from one side of resistor 1 to the other one, and from this side of resistor 2 over to the other side, which we would call V2, and from this side of resistor 3 over to the other side, which we would call V3, they're all the same. They're all exactly the same because they're all connected to the exact same wire on the left side and the exact same wire on the right side, okay? All of them have the same potential difference across them. Now, I'm going to redraw this circuit, kind of like we did the last one, in an effort to kind of help us understand that a little bit, okay? So let's take the exact same circuit and draw it sort of vertically. So I'm going to take that and let it sort of increase the voltage over here. So this is where we add some voltage. We go from V equals 0 up to some higher level, okay? We're pumping the water up to a higher level. And then let's just imagine we get over here somewhere and we do something like this. We say one resistor is here, and one resistor, I'm just going to make it curved just to do something different, goes there, and one resistor is over here. This is the exact same circuit. There's no difference at all. Okay? Now notice what happens with the current. It starts in one location here and works its way around. It gets to this point and it says, oh, I got 3 different ways I can go. This is almost like if you imagine like a big river that's approaching a cliff, okay? And it gets to the edge of the cliff and it's like, oh, there's some big rocks that are in the way such that it makes it divide, and it can like fall down the cliff over here, or it can fall down the cliff in the middle, or it can fall down the cliff over on the side, okay? It's all falling from the exact same height, going down to the same ground level. It's just got 3 different waterfalls that it's gonna fall over, okay? They're all exactly the same. So this potential difference, this height, is the same for all of them. The thing that's different is that some of the current goes this way, and some goes that way, and some goes over here, but all of them come back down together at ground level before they go around the loop again, okay? So V is the same for all of them. It's the current, the amount that goes down each path is different. Do you see how that works? Does it make at least a little bit of sense? Give me 40%. 40% sense? Can I have 50? Anybody want to go as high as 60? That's pushing it a little bit, maybe. I don't know. Okay? So let's work through this and determine what the equivalent resistance will be in this particular scenario. So first of all, the total amount of current is equal to the sum of all of the branches of current, however many there may happen to be. This particular circuit has 3. Okay? Once we have that, we can express each one of these a different way using Ohm's law. So I'm going to say first of all that V total over R equivalent, keep in mind that's just Ohm's law, V equals IR, we've just taken and solved for I, is equal to V1 over R1. That's the same thing as I1, and we're going to have V2 over R2 and V3 over R3. And then don't forget that V1 is equal to V2 is equal to V3. Those are all the exact same. So I'm just going to call them V, and that way we can factor them out of this. So then we have something that looks like this. I've got V times 1 over R1 plus 1 over R2 plus 1 over R3 equals V total, and I'm going to rewrite this as 1 over REQ. V total and V are also the exact same thing. So I could say this is also equal to the total, which means I can cancel those out. And then you have this expression for the equivalent resistance. The equivalent resistance is the reciprocal of the sum of the reciprocals. What I think to say that is. And if you worked through that with some numbers, you would discover that the more resistors I add in parallel, the less resistance there is in the circuit. The more we put in parallel gives me less total or equivalent resistance. That seems a little bit weird. I'm literally physically putting more resistors in the circuit, but because of the way I wired them up, I'm getting less opposition to the charge flowing through the circuit. I think that there's a way that I can explain this. Remember, we were talking about resistivity, and we had that idea where it's like there's a value for the material, but then if I take more of it and give more length that all the charges have to pass through, that's one way of increasing the resistance. But also, if I give it a narrower pipe, that also increases the resistance. It's like I'm trying to force a bunch of traffic through a little tiny narrow highway, okay? There's opposition to that flow. It doesn't flow through there as well. Well, essentially, by putting more and more of these resistors in parallel, it's almost like I'm opening up additional highways, okay? It's like there's 3 lanes of traffic, and it's like, let's make it 5 lanes of traffic. There's more that are in parallel. There's more room for the charge to flow through, which gives me less opposition, okay? More highways for the charge to flow through. Series and parallel resistors. Do you have questions about how this stuff operates? Anybody? Anything? Nothing at all. Are you sure? Should I keep asking? Is this irritating? Should I stop? I don't want to stop. I'm going to keep going. Little questions, little statements. Look at that. I made a question happen. What's up?
For the equivalent resistance, what's the difference between series and in parallel?
What's the difference between series and parallel?
For the equivalent resistance.
For the equivalent resistance in parallel, it's 1 over that equals the sum of these reciprocals. In series, you just add them. It's just R1 plus R2 plus R3 plus R4 plus however many you have. It's as simple as just adding them together, which is nice and easy. So you guys have something to be thankful for, believe it or not. Tomorrow, for another class, in the evening, from 7 to 9, I'm giving them an exam. At night on Halloween. It was beyond my control. Like the university said, this is when your exam will be scheduled. And I was like, okay.
You just hate your students.
No, I don't hate my
Wait, it's
students.
not after Halloween,
No, it was,
Okay.
this exam for this other class at this other school was literally like scheduled for me on Halloween evening.
Then they hate.
I feel like the whole thing should be themed kind of dark. Don't you think? Like I should come like dressed up as like the Undertaker, and like we should have like scary music that kind of plays in the background the whole time. Yeah, and occasionally, just while they're like focused on the exam, I just pop up out of nowhere, and I'm like, "Mwah!" And then they sweat a few extra tears.
For every person who makes scream, they get 1 extra point.
That kind of keeps me a little limited because I don't want to give out too many points.
Well, it depends
But
on
they
how many
get
people you
something
scare.
for being scared. Yeah.
It's like if you make them cry, then they get a.
Before I make them cry, you're assuming they're going to cry. They might just laugh at me.
Well, then they lose 5 points.
Yeah. Okay. I'm unsure what to do, but don't you feel like it's almost like having an exam on a holiday? Like I should do something, but I don't know what to do. I thought about just bringing candy, but there's like nearly 300 students in this particular class. That's going to get a little pricey. I can't just like randomly. I could just throw candy at people. Like I have like 20 pieces of candy during the thing, and I just stand up there and like they look like they're struggling. Yeah, that'd be kind of mean too.
Or show up with a bag with all their names, and then they get to pick their grade.
Ooh.
So they have to go up and pick a thing, and so it's like, oh, you get an F. Oh well.
Or they could choose one of two bags. This one has candy. This one has random grades. Would you rather have candy or maybe get an A without having to take the exam? That's, ooh, yeah. I don't know, if you think of any good ideas, let me know.
I like that one.
You like that one? Yeah? I don't think I'm allowed to do that. Someone would complain, being like, they got an A and they didn't even take the exam. I took the exam and got a C.
You can do it extra credit.
An extra credit exam?
No, just one part. One part will be like extra credit points, another one will be candy. So you'd be like from 1 to 3.
1 to 3 extra credit points.
Or
I
if they
kinda
do
like
a bag
that.
of candy, you get a
Or
too.
candy.
So they have to bring
They
it.
bring you some.
Oh, yeah, they should all bring me candy.
Yeah.
Like every one of them, if they just brought one little piece of candy, I get 300 pieces of candy.
Capitalism.
And then you get that.
Capitalism.
Yeah, and then you bring it us the next day.
Yeah, I don't know. I don't really have any good ideas. Nothing.
Or just
But I do think it
cancel
should
the
be
exam.
dark, just dark themed all around. Yeah.
I'm
I don't
gonna
know.
make it really hard. Just give them all that.
Just give them all Fs. Maybe the exam is already incredibly difficult, and each one comes with just a little bit of blood. I won't say from where. They just have a little drop of blood on them. No, I'm not going to do that. That's disgusting. I'm skipping some slides here. We may come back to some of them later, but I want to do the example problem. So, there we go. Still going. Where is it going to end up? Where is that example problem? There it is. Huh. That circuit doesn't look too bad. We're going to work through this one together. And then as soon as we finish this circuit, I'm going to give you one to work and give you like 15 minutes to work on it. And then I'm going to talk a little bit more. Okay? Sound good? So if you pay attention now, you're going to understand how to do the circuit I'm going to give you, and life is going to be good, and you're going to have one of your homework problems done, and that's going to be fantastic, and that's going to be way better than the way I'm treating this other class tomorrow. Yeah. So anyway, let's work this problem. Notice there's not much that's being asked here. Find the energy lost, and this isn't going to make any sense to us right now, but I'll explain, due to joule heating in resistor R2 in 15 minutes. Let me tell you exactly what that's talking about. Just first of all, ignore this word joule. You don't need to know anything about that. Here's what I will tell you that it's asking for. It's essentially asking for just the energy lost, okay? As current goes through a resistor, it gets a little warm, just like with a light bulb, right? You pass current through it, it lights up, it gives off light and heat because it gets hot, and there's some energy that's lost there. So, first of all, we learned about this equation. Remember, power is equal to I squared times R. Okay, we talked about that very briefly. And also, power is equal to energy divided by time. Energy divided by time. Let me move that down so you can actually see it. I always forget that things are cut off a little bit in here. Okay? So what we're going to do is find that energy is equal to power times time, which is I squared times R times time. But we only want to do this for resistor 2. Resistor 2, the one right there in the middle. Which means that, well, they gave us a time, 15 minutes. We know the value of resistor 2. It's given up here as 3.5 kiloohms. The thing I'm going to need to find is how much current is passing through that resistor. Okay? So I need I2 in order to be able to solve this. Okay? I need to find the current that's passing through resistor 2. And we're going to go through a whole sequence of events to find that. All right? So the first thing I need to do to be able to sort this out is to just simplify the circuit all the way down to one resistor, one equivalent resistor, one resistor to rule them all, if you want to think about it that way, okay? So we need to simplify the circuit by just finding parts that are in series and parallel and then slowly making the circuit all the way down to one resistor. So take a look at these 4 resistors and tell me a relationship between just 2 of them that you are 100% sure is true. Tell me 2 resistors that are either in series or parallel. Yeah? I would agree with that. R3 and R4, those 2 on the right, are in series. If you just imagine current arriving, say, at this location, I don't know how much, I don't know where it's coming from, none of that really matters. It's going to pass through resistor 3, and then it has no choice but to pass through resistor 4. Okay? So let's just start with simply that and say that R3 and R4 are in series. R3 and R4 are in series. To help ourselves out, I'm going to make a little note just underneath this. Remember that if they're in series, they have the same current passing through them. So whatever current is passing through resistor 3 is going to be the same as the current that's passing through resistor 4. And once I put them together, I'm going to call that the combination of 3 and 4. And that combination will have the same shared current as well. So I'm going to call that I34. R3 and R4 are in series, so they share the same current. Okay? So let's do the equivalent resistance part for just this. We could say that R34 is equal to R3 plus R4. In series, it's as easy as that. We just add them together. So let's look at the values that they gave us. Notice everything is in kilo ohms. So R3 is actually 2,000 ohms, and R4 is 1,200 ohms. So let's write those out. We've got 2,000 plus 1,200. So nothing too difficult there. R34 is 3,200 ohms. Okay, so that's the first step. Good so far? Not too bad? Okay. I'm going to redraw the circuit each step of the way so we can kind of see what's happening. It doesn't have to be neat. I just need a little sketch of where we stand with things, okay? So at this point, we could draw something like this. We've got our battery down here. We've got an R1 there and R2 here. And now we've combined those last 3 resistors, and we're calling that R34, okay? That's the circuit as it currently stands. Now, look at the new circuit and find another relationship between a couple resistors that you are sure exist. 2 of them that are in series or 2 of them that are in parallel. What's that? They're all in parallel? They're not all in parallel. I would agree with that. Yeah, there we go, okay? So let's trace this around just a little bit. Notice, this point that's actually marked, that's a dividing point for the current, okay? So the current can go around to the right side, or it can go straight through resistor 2, and that all comes back together at this point, okay? At that point, we've finished the relationship that's happening here, and it had nothing to do with R1. So we can say that R2 is in parallel with this other branch, which we combined as R34. Okay? Soak that in. Do you feel okay about it?
Wait, can you explain the dividing thing again?
Okay? So the current starts here, gets to this point, and then has options. It can travel along this path, or it can travel along that path. Both of those paths reconvene right there. Okay? So because R2 and R34 share this splitting point on one side and share the coming back together point on the other side, we can say that they're in parallel with each other. Okay? So let's go ahead and write that down. I'm going to go over here to the side. Ooh, where do I want to do this? Let's go ahead and do this right here. So we're going to say that R2 and R34 are in parallel. And what do they have in common if they're in parallel? Potential, voltage. So I'm going to write down as a note to myself for later that V2 is equal to V34. And once I put them together and combine them, well, they're still going to have the same points on both sides. So I'm going to say that that's also equal to V234, the combination of 2 and 3, 4. Okay? And then we're going to find the equivalent resistance for this combination. So I can say that 1 over R234, which is the combination of all three of those now, is equal to 1 over R2. Did you hear that? Anybody? No? You didn't hear it? You know, the thing about the stuff. No? I'll say it again, yeah. So we've got 1 over R234 is equal to, prepare yourself, 1 over R2. See, it's just there. It's subtle. Yeah, the D2 always follows the R2. You can't help but like it just, even if it's not verbally said, like just mentally. I know some of you are like freaking out, like there's ghosts. He's hearing things. What's happening? It's Halloween a day early. What's going on? No, there's just always a D2 that follows R2. Like it's just like, I can't not hear it every single time. So 1 over R2, see? It's just kind of, ooh, yeah. Plus 1 over R34, okay? And we'll plug our numbers in. We know R2. I should just train classes that every time I say R2, they're all like, D2! That'd be kind of fantastic. Scary for everyone, but it'd be kind of fantastic. So 1 over that, plus 1 over the thing we just found from just above, and then take the reciprocal after we add them. Somebody tell me what you get for R234. 1671. Let me see if that number is what I have here somewhere. 1671, that works for me. 1671 ohms. And then I'm going to redraw the circuit again. We have now combined these parallel branches on the right, and we've called that 234. So let's redraw this again with R1 here, and then we've got our battery there, and now over on this side we've got R234. And at this point it becomes pretty apparent what's left, right? Question?
So when you, so 3, 4, you obviously just added them together.
Yep.
But then did you like subtract? How did you get 2, 3, 4 again?
234 is from this equation. So 1 over R2, which is 3,500, plus 1 over R34, which is 3,200. Take the reciprocals, add them, take the reciprocal.
But you take the reciprocal of that?
At the end, because 1 over R234 is whatever this is.
Yeah, and then you're trying to find.
Trying to find just what's in that denominator.
Okay.
Okay? So be careful. If you're a little worried, that like maybe you just double check and make sure you get these same numbers if you're worried about the calculation. Okay? What's the relationship now? Once we like step through and redraw these, it becomes a little more apparent sort of like what's happening as opposed to trying to look at everything at the same time. The things that are left are in series with each other. So I can say that R1 and R234 are in series, which means that they're going to have the same current passing through all of them. So I1 is going to be equal to the current through I234. And really, like everything here is getting all of the current, right? Whatever leaves the battery is going to go through 234 and then go through number 1 and come back around. It can't go anywhere else. So really, I could just call this, well, 2 different things. I1234, if you really wanted to just kind of continue this notation. Now everything is in there. Or I could say that it is the total current. Okay, the total current is what's passing through each of these. This problem can be done sort of faster. I'm trying to be really explicit with it by going through each step. After you get a little practice, you might find like maybe you don't need to write all of these things down, but I think it'll help as you go back through and try to work problems on your own and do the homework, etc. Okay? So here at the end, let's add these things together. So at this point, we're finding R1, 2, 3, 4, which is really the total resistance. It's the equivalent resistance for the entire circuit. And it's going to be just the sum of R1 and R2, 3, 4. And looking back at our numbers, R1 is 570, R2, 3, 4 is what we just found. So you should get 2241, I think. That is the equivalent resistance for the entire circuit. I could take all 4 of those resistors out, just put the 1 there, same circuit. There is no difference between the two. Although you're thinking, why are we doing all this? I thought we were trying to find this one current through this one resistor. We're getting there. Okay? To actually get there, this is the first step you're really going to have to do every time. We need to find how much current there is, like in the circuit as a whole, before I can find out how much is going through one little part of it. Okay? So once we have that, let me just switch colors here so I can indicate that we're going to go use this other little space over here next. So I'm going to take this, right here. Okay? REQ, and I'm going to use this in an equation for the entire circuit, which is Ohm's law, and everything here is about the total. So we're talking about the circuit as a whole, the total voltage, the total current, the total resistance, okay? And I can solve that for the total current, which is going to be V total over REQ. And they told us V total is up here at the top. They use slightly different terminology, so let me rewrite that. Is 15, and REQ we just found to be 2241. Divide those, and what do you get? Hmm? 0067? Okay. 0067. An idea. Maybe all the answers on my final exam tomorrow night should just be 666. That'd be kind of fantastic. Or it's like hidden in the answer somewhere. Then people will be like, wait a minute. They get to the last problem, there's no 666 in their answer. They'll be studying a way, like there has to be a way to find it in there somewhere. That could be kind of dark. It's a thought. I think it's too late now. And I don't think there's anything I can do about it at this point. What's the unit here? Amps, 0.0067. That's the total amount of current that comes out of the side of the battery and begins to follow the paths that are laid out before it, okay? So starting right here, we have I total. And it's heading into that first splitting point where some is going to go through R2. Yeah, there it was again. And some of it goes through that other branch. We want to find out how much goes through that R2 branch, okay? So let's see if we can sort this out. And to do that, I'm going to add another slide, I think. Hey, look, I already had another slide here to do it. Why have I been trying to cram everything into such a small space? Look at that. I thought out things in advance. Weird. What's wrong with me? I don't understand. So let's see. We just discovered that the total current is 0.0067 amps. Go back and look at that previous slide and you'll see that we made ourselves a little note that tells us some other things that that current is equal to. That comes in handy, okay? I'm trying to work my way back to finding the current through number 2, okay? That's gonna help us out at some point, okay? So we know that I total, the number we just found, is also equal to this current through the combination 2, 3, 4. This combination resistor, all right? So let's put that in there as well. This is equal to I, 2, 3, 4. And then I'm going to start repeatedly using Ohm's law for different little parts of the circuit. So I can say that the potential difference across 2, 3, 4 is equal to I, 2, 3, 4 times R, 2, 3, 4. We're just applying Ohm's law, not to the whole circuit now, but to one little combination part of the circuit. In other words, looking back at our circuit, we're just applying Ohm's law to that resistor, okay? It's going to use whatever the potential difference is, the drop in potential as the current flows through that resistor, and it's also going to use how much current is flowing through there, okay? So if we go through this, what do I not know? I know this value for R, and I know this value for I, which means I can find V234. It's equal to 0.0067 times, what was R234? It's back there somewhere. 1671? Is that what we had? So V234 is what? 0.0067 times 1671. Go. 11 point, let's just say 2 volts. Question? 11.2 volts. So go back. Let me look at the circuit and figure out what we've discovered here. Basically, we know how much current is passing through that resistor, okay? Whatever current is passing through 234. And we found the voltage drop as we go from one side of that resistor to the other, okay? 11.2 out of the total of 15 volts is getting used up, which means that even though we don't need to know this, right? If it goes down 11.2 here, it's got to go down the rest of the way as it goes across that other resistor. How much voltage is left? It was up at 15, it went down 11.2. It's got to go the rest of the way. It sounds like there's 3.8 that will drop for this other resistor as it comes back around to the beginning, okay? All of these little parts of the circuit, like you should be able to come at it different directions and all the numbers sort of add up and make sense no matter which part of the circuit you look at, okay? So what do we know that V234 is also equal to? Let's go back to this. Notice V234 is the same as V34 is the same as V2. Now we've got something that's just about the resistor that I'm worried about, okay? So we can say that this 11.2 volts is the same as the potential drop across resistor 2 all by itself. And if you go back and look at that circuit in its entirety, that should sort of make sense, okay? 11.2 is the potential difference between here and here across just resistor 2, or across the combination of 3 and 4, or across the combination of all 3 of them. That's the potential difference between those 2 red dots. So once I have that, and now we're getting close, I can use Ohm's law once again and say V2 is equal to I2 times R2. And we can find the current through resistor 2. So I2 is equal to V2 over R2. That's 11.2 over R2, which is 3,500. And I've got 0.0032 amps for that one. Okay. Now, before I go any further, I still want to kind of point out how some of these circuit parts are fitting together. Remember we said the total amount of current here was 0.0067. We just found out that some of that went this direction, right? 0.0032 goes through resistor 2. But some of it keeps going straight, right? How much of it keeps going straight? Yeah, 0.0035, right? The amount that's there has to stay the same. So the total amount of current stays the same. Some of it goes off one direction, some of it goes the other direction, and then they add back together over here. And once I get to this point, it's back to 0.0067, and that's how much would go through resistor 1, okay? Literally see it like these streams of current. There's a certain amount that can't get any more and I can't lose any. I should be able to track where all of it goes through the different branches, okay?
Is the resistor basically like kind of slow down or something? Like,
What does it do? You can think of it as sort of consuming a little bit of energy through collisions.
So it is using some
It's not using current. It's
losing some.
It's not losing current because once I get to the other side of resistor, same amount's still there. It flows through. It maybe just has some difficulty getting through.
So it just takes more time to get through, right?
I don't even know if time's the right term. Think back to the waterfalls. Okay, if you imagine a waterfall as just simply a drop from one level to another, like as that water falls, you can imagine it like is going at one velocity and it like speeds up, and like I could put an object in there and it could turn it and do work and things. That's essentially what all the electrical devices are. There's something the current can flow through, and as it flows through, it can make things happen. It's that opposition because of collisions at the microscopic level that essentially is exerting forces on things and physically making things occur. Okay. Where does this leave us? Where are we in this problem? Let's go back. What are we looking for? This thing up here. Energy is equal to I squared times R times T. And that's going to tell me how much energy gets used up by resistor 2 specifically over a period of 15 minutes, okay? So at this point, we can say that energy is equal to I squared R times T, and we're specifically looking at the second resistor. So I'm going to put a subscript 2 on everything. We now know this is 0.0032. We're going to square that. Resistor 2 is 3,500. And to be consistent with the units, I can't use minutes. That's not a proper SI unit. Instead, I need that in seconds. So 15 minutes times 60 seconds, we'll get that into seconds. So we're going to write that as 15 times 60. And if you put all that together, you should get about 32 joules of energy. 32 joules of energy. That's a lot of stuff. You will find as we progress through chapter 28, there are essentially 3 main problem types, and you'll see that reflected in your homework as well. There's series and parallel resistor circuits, being able to sort of analyze every little part of it, okay? We're going to have like a little bit more complicated, I'm sorry to say that, version of this that are called Kirchhoff's laws. We're going to use some of that. I'll have to teach you that next time. And then there's circuits that have both resistors and capacitors in it. There's like 3 main problem types, okay? So what we're going to do, it is 4:24. I'm going to take just the next few minutes till about 4:30 to go back and we'll deal with some of these multiple choice questions, and then for the remaining amount of time, I'm going to give you a similar problem to work from your homework. So let's go right here. And with this basic little circuit with just 2 resistors, can you figure out how much current goes through resistor 1? Take just a second. It might require just a couple of real quick mental calculations, but it should be something you can figure out based on our rules for parallel resistors. Anybody think you have the answer? Yeah, it may not be as hard as you thought it was at first glance. Resistor 1 and 2 are in parallel. They have to have the same voltage or potential difference across them, which is 10. Everything is 10 here. Total is 10. And since everything is in parallel and nothing else is happening, you can imagine like V1 is 10, V2 is 10, everything is 10. So if I'm looking at resistor 1, I can use Ohm's law. V1 equals I1 R1 and solve for I1, which is V1 over R1, which is just 10 over 5, which is 2 amps. Okay? One little circuit that is a piece of a bigger problem that you might have later. Let's see. This is a little bit difficult to understand, but what they're trying to say is that we have some resistors in parallel, and we're just going to keep putting more and more in parallel, okay? What happens to how much current is in the circuit if I put more resistors in parallel? Goes up, but why?
Because there's more pathway.
Yeah, exactly. So we could think of this a couple of different ways. There's more pathways for charge to flow, which essentially means that Req goes down. The equivalent resistance as I put more and more in parallel goes down. And if the resistance goes down, there's less opposition. That means the current can go up. More current because less opposition. Good. Let's see. Notice this terminology at the top, something perhaps a little bit new. What do you think? Yeah, the one vote that I heard out there, number 3. All of the current will go through the wire, okay? If we assume that the wire has no resistance, or at least it has way less resistance than the light bulb itself, okay? It's kind of like the charges get to this point, and they literally follow the path of least resistance, right? It's like all of a sudden we're using common phrases and as it applies exactly to an electrical circuit. They get to this point and they're like, hey, no opposition that way, or I can fight my way through this light bulb. I'm just not even going to bother with the light bulb and we'll go the easy way, all right? Also, you could think about that in terms of two things being in parallel. Essentially, I have a wire of no resistance that's in parallel with a light bulb that has some resistance. The amount of current that goes down each parallel path is based on how much resistance is there. The ones that have less resistance are going to get more of the current. The ones that have more resistance are going to get less of the current. This is just sort of an extreme case, so all of it goes one direction. Yeah.
So if you have an entire parallel circuit and then you add in another wire that encompasses all of that, it will just cut out everything that's in that circuit and just go over the
Yeah. And that is what we call in common nomenclature a short circuit. We gave it a shortcut around the path, which means it doesn't have to encounter any of the resistance that's there.
Does that mean that you could also use a switch?
Use a switch? We could do a situation where like I could put like a switch here, and then as long as that switch stays open, everything goes through the light bulb. But as soon as I close the switch and make the connection, then all of it goes around the light bulb. Yeah.
Is that basically how it works? Like the switches are
Roughly speaking, yeah. I mean, circuits generally aren't quite that simple, but yeah. Another way of doing that is just like forget the wire. You just put a switch right here, right? It's like, okay, I can't get to the light bulb, I can't get to the light bulb.
So the short circuit that would result from like water and electronics, does that just mean the electricity is going into the water?
Yeah. It's going into the water, and that means it's going, probably making connections that it should not make because it's going through the water instead of the predefined paths in the circuits. Okay?
So does water have low resistance?
Water has lower resistance than most electrical components. It turns out if the water is extremely pure, which no water we encounter is, then it has high resistance. It can't flow through ultra pure water. So it's the impurities that give it some.
Ions in the water.
Are you ready to try a problem? We've arrived at 4:31. So we're going to deal with some, I like these answers though. Glow brighter, glow dimmer, explode is the last one, which, yeah, that's probably not correct. But I'm going to slide over to another file here. One of your homework problems looks something like that, okay? It's a little bit of a tricky circuit to sort out. Be very careful and trace the current, trying to figure out what's in series and parallel. Before finding this particular current, you're going to need to do something earlier. Let's just call it part 0. Find REQ. Just follow the steps that we did on that other problem, and you should be able to sort it out. Redraw the circuit each step along the way. If you think you have part of it done at any point, want me to check your work, I'm happy to do that before you proceed.